For an example of these higher order derivatives, I would like to consider the following example. Find the first 4 derivatives of f of x is equal to x cubed minus 7x. Great way to take 4 derivatives is to start with one of them. So we'll take f prime of x to be the limit as h approaches 0 of the difference quotient for f, which will look like the following. The limit as h approaches 0 of f of x plus h, we replace all of our x's with an x plus h, and then we subtract the original function. There will be a lot of expanding that takes place at this point. For x plus h quantity cubed, please be aware that what I mean is x plus h times x plus h times x plus h. When fully expanded, using proper algebraic techniques, it will look like the following. X cubed plus 3x squared h plus 3xh squared plus h cubed. Then we can distribute the minus 7. We'll get minus 7 minus 7h. And distribute this negative sign as well to get negative x cubed plus 7x. This will all be over h. Then, take a look for any like terms that can be combined and canceled. I'm seeing an x cubed minus x cubed and a 7x minus 7x. Everything that's left over, you'll notice, has an h in common. So as we've done on previous examples, I am going to factor that h out. Factoring out that h is going to leave me with 3x squared from here. From here, that'll be plus 3xh. From here, that'll be plus h squared. And finally a minus 7 from the minus 7h. Canceling these h's and applying the direct substitution property in that order gives us 3x squared minus 7. These other two terms will go to 0 as h goes to 0. So as a reminder, this is f prime of x, the first order derivative of this function. For a second derivative, we'll be taking the first derivative of the first derivative. So we'll be setting up the limit as h approaches 0 of f prime of x plus h minus f prime of x all over h, which is a fancy way of saying do exactly what you just did, but do it to this function. That'll be the limit as h approaches 0 of 3 times x plus h quantity squared minus 7, that's our f prime of x plus h, minus the original f prime, 3x squared minus 7. We'll put that whole thing over h. I'm going to do 2 algebraic steps in this next step. I am going to expand x plus h quantity squared and distribute the 3 to the result. If you'd like to try this for yourself, please feel free to do so. The result that you get should be 3x squared plus 6xh plus 3h squared. Distributing the negative sign to the second set of parentheses, we'll get minus 3x squared plus 7. At this point, you should see some things cancel out, specifically 3x squareds and the 7s. Everything left in the numerator has an h in common. So I'm going to factor it out. 6xh would become 6x, and 3h squared would become plus 3h. At this point, you can cancel out the h from the numerator and the denominator, and then use the direct substitution property to allow h to go to 0, leaving you with 6x. That, of course, is our second derivative. For a third derivative, we'll be taking the first derivative of the second derivative. That'll be the limit as h goes to 0 of f double prime of x plus h minus f double prime of x all over h. This will be the limit as h approaches 0 of, our function is 6x, so this will be 6 times, oh boy, That pen is dying. Well, killed another one. Good on us. It's a good thing I always have a spare. So that'll be 6 times the quantity, x plus h, minus the original function, 6x, all over h. We can then distribute the 6 in the numerator to get 6x plus 6h minus 6x all over h. In order, I am going to combine the like terms of 6x and minus 6x. Then I'm going to cancel 6h divided by h. That is going to give us the limit as h approaches 0 of 6. That, of course, is simply going to be equal to 6. And this is what our third derivative is equal to. Finally, for a fourth derivative, and this will be a nice quick one because derivatives of constants tend to happen really quickly. This will be the limit as h approaches 0 of f triple prime of x plus h minus f triple prime of x all over h. However, our function is constant, so it doesn't matter what the input is. The output is simply going to be 6. Simplifying 6 minus 6 gives us 0. 0 divided by something that is approaching 0 is going to be exactly 0. Wait, that's a smiley face, not 0. Never mind. 0. So, now that we've been through 4 derivatives for one single function, wouldn't it be great if we could develop some sort of shortcut so that we wouldn't have to do all of this stuff? That right there is a great transition to our next section.